Hello everyone, hello dear students, very good evening to all of you. So welcome to the Power Hour session, and today I am going to deal with a very important topic, that is electrostatics. I'll be giving you key concepts and I'll be discussing few questions that will help you to understand the key parameters of this chapter. It's a very important topic, electrostatics, and every year in NEET exam some of the questions are being asked from this topic. So just tell me if I am audible clearly, am I visible clearly to all of you? So just you can send me a text message on chat so that I can start with the session. So those who are online, they can help me to understand whether I am audible clearly, am I visible clearly? Okay, fine. So let's proceed with our session today without wasting any time. So as you can see, electric charges in field, that the topic electrostatics I am going to discuss today. So we have to mention the topics that I am going to cover over here. So I'll be covering up Coulomb's law. Then I'm going to discuss about the electric field and electric potential. I am going to discuss about the concept of electric dipole, and then electric field and electric potential due to electrodipole. So when I'm discussing about the electric dipole, I'll be covering up all the topics that are related to electric dipole, that if you have to write down electric field, electric potential due to an electric dipole, you want to write down the potential energy of an electric dipole, you want to write down the torque which is experienced by this electric dipole in an external magnetic field. So all those topics that we have to cover. So covering Coulomb's law, electric field and potential, electric dipole, and then one topic is conductors. So this entire chapter can be broken into these 4 subtopics. So if you can understand these topics, then you are good to go with this chapter, okay? So I'll be starting with Coulomb's law. So when I'm talking about Coulomb's law, quickly I'll write down the important concept, that Coulomb's law is a law which gives us the force between two point charge particles, okay? So we can apply this Coulomb's law only for point charge particles, and in some cases the result can also be extend up to some different conditions as well. But primarily you have to understand like this, that this law should be applied for only the point charges. If it is not point charge, then you cannot apply this Coulomb's law directly, okay? Let's say I'm having one charge here which is distributed along this rod. So let's say this is one charge body and it is having charge Q1, and I'm having another charge body which is having some charge Q2, okay? So I'm having these two charge bodies which are having charge Q1 and Q2, and you can see that these are not the point charges, okay? Since these are not point charges, I cannot directly apply the Coulomb's law in this condition, okay? So you have to understand this thing, that whenever we have to apply Coulomb's law, primarily we are going to apply it for point charges. In some conditions it might be applied in other conditions as well, but right now I'm not going to discuss that. So just make it understand very clearly that initially we are going to apply it only for point charge particles. So applicable for point charges. And why we are using this Coulomb's law? To calculate the force between charge particles, 2 point charge particles. To calculate force between point charge particles. So we can calculate the force between point charge particle using the Coulomb's law. So what is the expression? The expression states that if I am having charge q1 here and another charge q2 here, and the distance between these two charges is, let's say it's r, and both are the point charges, q1 q2 are point charge, and the distance between them is r, then force between, and the medium I have taken to be vacuum or air. Okay, so I have taken that both the charges are placed in vacuum or in air. So in electrostatics, for us, vacuum and air is almost the similar thing. So there is no difference in vacuum and air as far as our electrostatics is concerned. Till the molecules of air are not polarized, till that time vacuum and air are same thing for us. So q1 and q2 are point charge particles which are separated at r distance, and the medium being vacuum or air. So in this case I can write down force to be q1 q2 upon 4 pi epsilon naught into r square. This is the magnitude of the force. This is the magnitude of the force of interaction between the two charge particles. Okay, so you can see here that I have written one quantity epsilon naught here. So you know that epsilon naught is what? This is electrical permittivity. Electrical permittivity of the medium. So this value depends on the medium. So if you will change the medium, then this value will also change, and for a given medium this value will remain constant. So in this case, electrical permittivity of the medium is epsilon, but we are talking in this case about the medium being vacuum or air. So epsilon naught represents the electrical permittivity of vacuum or air. Okay, and for other mediums I can simply write down epsilon, right? This will be electrical permittivity of a given medium. Okay, so for air and vacuum I write a very unique symbol, that is epsilon naught. So that will be for air or vacuum, and for remaining all other mediums I'll be directly writing epsilon. Epsilon represents permittivity of the given medium, and we know that epsilon is the absolute permittivity of the medium, and it is written as epsilon naught multiplied by epsilon r. You know that epsilon naught is what? It is the permittivity of the vacuum or air, and epsilon r here is known as relative permittivity of that medium with respect to air. Okay, so epsilon r is what? It is relative permittivity of the medium. So this is permittivity of the medium with respect to air. I have taken air or vacuum as my reference, and with respect to that medium, if I am defining the permittivity of any medium, that will be known as relative permittivity. So that relative permittivity epsilon r is what? Epsilon divided by epsilon naught. So in all these cases you can see that epsilon r is not having any dimension, it is not having any unit, because it is the ratio of two similar quantities, permittivity of that medium and permittivity of vacuum. So the units will get cancelled, the dimensions will get cancelled, and it becomes unitless and dimensionless. So in NEET exam they can ask you sometimes about the dimensions and the units. So you should understand that this is dimensionless. The expression for the force is, I have written here, this is the magnitude of the force. So if the charge particles are placed in air medium, the force is q1 q2 upon 4 pi epsilon naught r square. And there is a fixed value for epsilon naught. You might remember that value if you have seen that, 8.85 into 10 power minus 12. This is the value of epsilon naught. Q1, Q2 are the charges, R is the distance. So this way you can calculate the force. If let's say I am writing the force between two charged particles, if I am writing the force between two charged particles, then let's say this is the case. I am having the distance R, the charge being same Q1 and Q2, and now this is some medium, and for that medium the permittivity is given as epsilon, and it can be written as epsilon naught epsilon R of that medium. Now again, if I have to write down the force, so the thing that you must understand is that electrostatic force between these two charged particles remains same irrespective of the medium. What changes is the net force on the particle will change, okay? Because what happens when there will be some medium between the charged particles, then due to the electric field, some of the particles will get polarized, and due to the polarization of the medium, some electric field will be induced, some extra electric field will be produced due to the polarization of the molecule, and because of that, the net force on any one of the charges will change. If I'll see the net force acting on Q1, that will change. The net force acting on Q2, that will also change. But the electrostatic force between these two will remain same. If I am saying you the force acting on Q2 because of Q1, so that will be same, K Q1 Q2 by R square. But if I am asking you the net force on Q2, that will change, because one force will be exerted by Q1 and another force will be exerted by the charges that are produced as a result of polarization of the medium. So that is a different story. So in this case, if I'm just writing the force on Q2 due to Q1, so that will remain same as the earlier situation. But if I'm writing the net force on Q2 due to Q1, so now that force will be what? I'm writing this force to be F dash, and this is Q2 Q1 divided by 4 pi epsilon naught epsilon R into distance square, okay? Now if you will see this result, Q2 Q1 upon 4 pi epsilon naught epsilon R into R square, so all terms are same as in the previous situation. This epsilon R is the only new term here, okay? So Q2 Q1 by 4 pi epsilon naught R square, that is F, and divided by epsilon R. So if you write down the net force acting on any one of the charge, that will be the force which we have already calculated when the charges were placed in air medium or vacuum medium, divided by epsilon R, that is the relative permittivity of that medium. So if you will divide force in air divided by the epsilon R, then you will get the net force acting on Q1 or Q2. So this is something you should keep in your mind, okay? So sometimes you people can end up doing some mistakes, so you have to just be cautious in this kind of situation. That you have been asked to calculate the net force acting on the particle, or you have been asked only to calculate the force on Q2 because of Q1. So force on Q2 just because of Q1 if you are writing, then this situation and the previous situations are identical. But when they are asking you to find out the net force on Q2, then it will change. It will become force in air divided by epsilon R. Now one more thing, that sometimes if required you can also write down these forces in terms of vector form. So let's say this charge is Q1 and this charge is Q2. So I'm writing in vector form. I'm writing this in vector form, okay? So Q1 and Q2 are the two charges we are having, and the distance is R, and I'm calling this as R vector, okay? I'm calling this as R vector. And you know that the like charges repel each other, and unlike charges attract each other. So electrostatic force is having two type of nature, that this force can be repulsive in nature or it can be attractive in nature. So if both the charges are of the same type, both are positive or both are negative, so in such cases there will be a repulsive force of electrostatic repulsive force. And when one of the charge is positive and the other charge is negative, then the force acting between the two charge particles will be of attractive nature. It will be attractive in nature. So in this case, if the distance is r, and let's say this point is a and this point is b, so the position vector of q2 with respect to q1 is r vector. Now I can see that whatever the force is being acting on q2 because of q1 will be repelling it forward. So the direction of force will be here, okay? This will be the force acting on q2 because of the first particle. So I am writing this as F21. So F21 is what? This is the force acting on the second charge particle because of the first charge particle, and the direction will be along AB, and direction will be away from A, So if I have to write down this in vector form, I can write down this to be F21 equals to what? The magnitude of the force, that is Q1 Q2 divided by 4 pi epsilon naught r square. This is the magnitude of the force. Now I have to write down the direction. So you can see this is r vector. So this direction can be written as what? R cap. The direction can be written by a unit vector. Okay. So if I am calling the vector from A to B as r vector, then r cap can be written as its direction. So I can multiply with r cap. So this will be now in vector form. Because if I am writing force to be in vector form, then I have to write down a magnitude and its direction. So this part is the magnitude of the force and this r cap is representing its direction. So direction is r cap. R vector is what? A vector from A to B. A vector from A to B. Now this can also be written like this: Q1 Q2 divided by 4 pi epsilon naught r square, and then this, this r cap can be written as what? R vector divided by mod of r. Yes or no? If you remember the results of vector, then you can understand that this r cap unit vector can be written as r vector divided by its magnitude. And by writing this way, this expression comes like this: Q1 Q2 divided by 4 pi epsilon naught r cube into r vector. Okay. So this is F21 vector. This is F21 vector, force on the second charge particle because of the first charge particle. Now similarly, if we will calculate the force on first particle because of the second particle, this force direction will come in this way. So this is force on the first particle because of the second particle, and you can see that this force and this force are opposite in direction. Magnitude of the force will remain same. So if I will be writing F12 vector, okay, F12 vector, this will be what? Same in magnitude but opposite in direction. So I can write this to be minus F21 vector. I hope this is clear to everyone. So whether they are asking you to find out the force on second particle due to the first, or force on the first particle because of the second particle, magnitude of the force will remain same. Direction will be 180 degree opposite. So that's why I put a negative sign here. Okay. F12 vector is negative of F21 vector. So this is how we can write down in vector form, in magnitude form. And the very important thing is that if there are more than two charge particles, okay, then we can apply the superposition theorem. Superposition theorem states that, let's say I'm having a charge particle here. Let's say this charge particle is Q1, okay, and I'm having particle Q2, Q3, okay, Q4, and many other charge particles. So let's say if I'm having one charge particle placed over here, and Q2, Q3, Q4, like this many charge particles are placed here. If I have to write down the net force on one, so I can use the superposition theorem, because this charge particle is going to experience a force because of the second particle, it is going to experience a force on the third particle, and it is going to experience a force because of the fourth particle. And so if other charge particles are also there, then it is going to experience a force because of all those individual charge particles. So how do we calculate the net force on 1? So the idea is very simple, that you write down the force on 1 because of 2, forgetting about the presence of Q3 and Q4. You have to forget about all the other charged particles. You just consider that Q2 is the only particle which is placed here. Write down the force on 1 because of 2. Then forget about Q2, Q4 and all other particles and just consider that only Q3 is present. Then assuming that Q3 is the only charged particle present here, write down the force on 1 because of 3, and similarly forget about Q2 and Q3, assuming that Q4 is the only charged particle present here. Write down the force because of the fourth particle on 1, and then add all the forces in vector form, and you will get the net force. Okay, so superposition theorem states that you can calculate the force due to each individual particle, forgetting the presence of all the remaining charged particles, and then all these individual forces are vectorially added, and then you will get the net force. So when I am writing the net force acting on the particle, I will be writing force on first particle because of the second particle F12 vector, plus force on first particle because of the third particle, then force on the first particle because of the fourth particle, and so on and so forth. So this is superposition theorem. It's a very, very interesting thing, and it helps us to calculate the force in different conditions. Superposition theorem. Okay, so you can calculate the force on one particle because of all the charged particles one by one individually, and then you can add them vectorially to get the net force. This is the idea. Using this idea, we can solve few problems, we can deal with few questions, and then we are good to go. So let's discuss one problem here. This is a very general problem that you might have gone through, but just for the sake of understanding it better, this idea will help you to understand the concept of superposition theorem. Let's say this is an equilateral triangle where the length of each side is A, and since it is an equilateral triangle, all the inside angles are 60, 60, 60. This is 60 degree, this is 60 degree, and definitely this also 60 degree. This is an equilateral triangle. So what I am doing here is, I am placing 3 identical charged particles Q on each corners of this equilateral triangle, and now I am supposed to find out the net force on any one of the charge. So let's say I have to find out the net force on this charged particle. So I'll try to find out the net force on this charged particle. So I can see that apart from this charge there are 2 more charged particles. So this charged particle is going to experience a force because of this plus Q charge, and it is also going to experience a force because of this Q charge. Let's say name A, B and C. Okay, so I'm going to experience force on A because of force this charged particle A is going to experience a force because of the charged particle C, and it is also going to experience a force because of the charged particle B. So I have to write down the force because of C and force because of B, and then I'll add them vectorially to get the net force on the charged particle A. I hope this is clear to everyone. So I can say that the net force acting on A is what? Force acting on A because of C in vector form, then force acting on A because of B in vector form. Doing this, I'll get the net force. So whatever may be the situation, the charges are arranged along a square, or they are arranged along a rectangle, or they are arranged in any manner, any form, I have to just apply the superposition theorem. That's it. And once you apply the superposition theorem, then only mathematics is there. You have to solve those mathematical equations and you can get the final answer. So in this case, I'll show you how I'm going to write down these expressions. Okay, so vectorially I have to add them, and you know that this charge is Q and this charge is Q and the distance is A, and this force can be written as force on A because of C. I'm writing only magnitude part first I'm writing, okay. So this is, that term 1 by 4 pi epsilon naught. This can also be written as K, and this K is known as electrostatic constant. This K is also known as electrostatic constant. And for air, the value is 9 into 10 raised to the power of 9. This is the value of K, electrostatic constant, and K is what? 1 by 4 pi epsilon naught. So we know that the value of K. So wherever 1 upon 4 pi epsilon naught was written, I can only replace it by K. So this is K, Q multiplied by Q, divided by distance square, that is A square. So this is the magnitude of the force, okay. And if I am writing the magnitude of force on A because of B, then also the charge is Q and Q here. So it is K, Q square by A square. This expression is also same. K Q square by A square. So the force on A because of C and because of B is equal in magnitude, okay, and I am writing this to be F, okay. I am writing this to be F. So now on the particle A, there are two forces acting. Both are having magnitude of F, where the value of F is KQ square by A square, but the direction is not same, okay. You can see that this force is acting along this line and this force is acting along this line. So this is what? This is force on A because of C. So this is FAC vector, and this is force on A because of B, FAB vector. So these two forces are having magnitude to be same. If I am writing the magnitude, it is F, this magnitude is also F, but the direction is not same. And I know that these two vectors are acting at an angle of 60 degree. This angle is 60 degree and vertically opposite angle. So this angle will also be 60 degree. So these two forces which are equal in magnitude are acting at an angle of 60 degree. So just by using the concept of vector addition, I can find out the resultant of these two forces. So the resultant force FA will be what? Under root of A square plus B square plus 2AB cos theta. So this is F square plus F square plus 2AB. So 2F into F, that is 2F square into cos of 60 degree, okay. The value of cos 60 degree is 1 by 2. This will get cancelled. And this is under root of F square plus F square plus F square. This is 3F square. So this is become F root 3. So the net force on A is what? F root 3. What is the value of F here? The value of F is this one, okay. So the net force acting on A is what? Root 3 multiplied by F, where F is KQ square by A square. So this is how we calculate the force acting on a particle due to the presence of other charged particles. And this idea can be extended to shape where a rectangle is there and all the corners of the rectangle some charges are placed, or the problem might be different, like I have taken all the charges to be positive in this case, but I can make one charge to be negative. Then what will happen? This charged particle will create a force in this direction, and since this is a negative charge particle, it will create a force in this direction. Then I have to find out the resultant of these two forces. So this angle is 60 degrees, so this angle will become 120 degree. So again, you know the forces, you know the angle, you can find out the resultant under root of A square plus B square plus 2AB cos theta. So these are some modification that can be produced in the problem. These are the modifications that can be done in the problem, and they can ask you to solve this type of questions, okay. So this is the approach that we should follow, that we have to apply the superposition theorem. We have calculated this and we have added them vectorially. Coming to the next part. So after discussing this problem on electrostatics, and I have explained you the Coulomb's law, there may be some different type of problems that can be asked from here, and there are some results, direct result, that what happens in case we are having, let's say I'm having a infinite length wire, and I have given a charge on its body, and let's say the charge density is lambda. So lambda generally represent what? Length, charge per unit length, okay? Let's say Q and the length is L. So Q by L is what? Charge per unit length, that is lambda. And here in this case I am assuming that lambda is a constant. Lambda is a constant. So if lambda is a constant, this is an infinite wire. After at a distance r from here, if I have to write down the electric field at this point, so that will come out to 2k lambda by r. This is the formula for the electric field produced by this linearly charged infinite length wire, okay? So this is like we are discussing about the electric field due to different charge distribution, okay? Different charge distribution, okay? Electric field due to different charge distribution. So there are two methods to obtain this result. One method is with the help of integration we can find out this electric field, and the other approach is by using the Gauss law. So what does the Gauss law states? Gauss law states that when I am writing the flux integral E dot ds, so that should be equals to net charge enclosed by the Gaussian surface divided by epsilon naught. So in this case, this is your wire, okay? This is infinite length wire. So I'll draw a Gaussian surface here, okay? I have taken a Gaussian surface, and you know how to calculate this flux. This is the flux, okay? Electric flux. How do we calculate the electric flux? This is electric field multiplied by area. Electric field multiplied by area. This is the most simplest way of writing the electric flux. So electric field multiplied by area, that will give you the flux through that given area, okay? Sometimes the electric field is not constant. If the electric field is not constant, then we have to write down the flux d phi through a small area where the electric field can assume to be constant for some time. Then it will be integral E dot ds, okay? And then we'll integrate this result, integral E dot ds for every small element. So when we'll integrate E dot ds for every small element and then we'll add them together, we'll get the total flux through that surface. So when I'm talking about the electric flux, what do you mean by that? When I'm talking about electric flux, it simply means that it is just kind of representing the number of electric field lines crossing through that given surface area. So let's say that if I am having this as one surface, and let's say the electric field lines are coming from this direction, okay? So when my hand is placed here like this and electric field lines are coming here, so this entire surface is exposed to the electric field lines, and this is the situation when maximum number of electric field lines will cross through my hand. But just assume one situation when I have rotated my hand by 90 degree and now it's like this, and just ignore the thickness of this hand, okay? So we are just considering a plain lamina, very thin lamina, a paper like thing, okay? So it is placed like this, and then electric field lines are coming. So electric field lines will cross parallel to this surface, okay? Will cross parallel to this surface. In this case, what will happen? There is no electric field line. There is no electric field line which is crossing through this surface. So in this case, the flux will become 0, okay? So that can be written mathematically by multiplying E with A. Multiplying with E with A. And if you want to write down that in vector form, that flux thing, it should be written as integral E dot ds, where E is the electric field, and ds is the small area through which we are interested in calculating the flux. So E dot ds will give you the flux, okay? So this is Gauss law, which states that integral E dot ds, okay, with the total flux through the Gaussian surface will be equals to net charge enclosed inside the Gaussian surface divided by epsilon naught. So in this case, if you'll see that I have taken one Gaussian surface. So Gaussian surface is a closed surface. It's an imaginary surface. And let's say this length is L and charge density is given as lambda. Charge density is given as lambda. Now you can see that the electric field lines will cross like this, okay. There is no electric field parallel to the wire, okay. There is no electric field parallel to the wire. So no flux from this upper surface and from this lower surface. All the electric field lines are passing only through the curved surface area of this cylindrical Gaussian surface, okay. So I am having this curved surface area. So all the field lines are crossing through this curved surface area of the cylinder, not from the circular cross section, okay. So in such situation, what I can do here is I can write down the net charge enclosed, okay. So the net charge enclosed is what? See here, lambda multiplied by length. Lambda is charge per unit length, then I am multiplying with length L. So this is the charge which has been enclosed inside the Gaussian surface divided by epsilon naught, okay. This is the total flux, and this flux will be equated to what? Integral E dot ds. And everywhere on the curved surface area the electric field is constant, so E will be taken out, and then we have to integrate integral ds. So integral ds represents the total surface area of the Gaussian surface, okay. So this is the curved surface area which is my Gaussian surface. So the total area of this Gaussian surface is what? 2 pi r into h. 2 pi r into h. So let's say this distance is r. So this is 2 pi r multiplied by L. 2 pi r into L. Now equating these two terms, I am getting what? Lambda into L by epsilon naught equals to E multiplied by 2 pi r into L. L will get cancelled. And what I am getting E to be lambda divided by 2 pi r epsilon naught. Lambda divided by 2 pi r epsilon naught. Just multiplying it with 2 in numerator and denominator, I can see that this becomes 4 pi epsilon naught, that is k. So 2k lambda by r. So this is the expression that we have got. So just like I have given you one example, there are certain different arrangement where we have to find out the electric field due to the given charge distribution. So one is this case, then we have finite length wire, then we have spherical conductors, solid conductors, hollow conductors, and a plate will be there, rectangular sheet will be there. So we have to find out the electric field due to different circumstances, different charge distribution, and then you have to remember those formulas, okay. So if you have, so we have completed two parts. We have done with the Coulomb's law, we have done with this electric field part. I have given you one example, and then you can go through the other examples as well, how the electric field has been calculated in those cases. Once you have done this, let's proceed with solving few questions, so that will give you a better idea. Now just see this question, that it's been given that two positive ions each carrying a charge q. So we have the same charge on both the ions, are separated by a distance d, and if F is the force of repulsion between the ions, the number of electrons missing from each ion will be what? So how we create an ion? Let's say this is an atom. This is an atom we are having, okay. So from this atom, if some electrons are lost, okay, some electrons are lost, then it will become what? It will become positively charged ion. So let's say n number of electrons have gone out from here, n number of electrons are taken out from this atom, so it will carry a charge of n into E. and that will be a positive charge. I hope you understood this. So when n number of electrons are taken out from an atom, it will carry a total charge which is plus n into E. It will be positively charged and it will be known as ion. So we have two ions, and these ions will be considered as point charge so that we can apply the Coulomb's law. So this is having charge plus Ne, this is also having the same charge plus Ne, and they are separated by a distance of d. So this distance is d. So when I am writing force here, it is K Q1 Q2 by R square. Q1 is N into E, Q2 is also N into E, becomes square K Q1 Q2 upon distance square. This is the expression. Just simplifying it, K into N square E square by D square. From here we have to find out the value of N. So that can be written as N is what? Fd square, F into D square divided by K into E square, and then I have to take a root, and then they have written all the expression in terms of 4 pi epsilon naught. So this K will be written as 1 upon 4 pi epsilon naught, that will go up. So 4 pi epsilon naught Fd square by E square. This is the value of N. This is the value of N. So what is the correct answer? Which of the option is clear? Correct. 4 pi epsilon naught Fd square by E square. 4 pi epsilon naught Fd square by E square. And that should be in the root. So these two are wrong. D is the correct answer. Okay. So D is the correct answer for this question. I hope you understood this one. Moving to the next question. Now. It's written that an electron is moving around the nucleus of an hydrogen atom in a circular orbit of radius r. The Coulomb force F between the two is. So let's say this is the situation. An electron is moving around the nucleus of an hydrogen atom. So let's say this is the nucleus. So nucleus is positively charged, and an electron is moving, right? An electron is moving. So here the charge will be due to only one proton. So the charge I am writing to be E here, and the charge of electron will also be E. This will be positively charged and this will be negatively charged, but magnitude wise both the charges are same, because we are talking about the hydrogen atom. In hydrogen atom, in the nucleus there will be only one proton and there will be only one electron, because its atomic number is 1, and they are revolving in circular orbit. And why they are revolving in the circular orbit? Because this is negatively charged and this is positively charged. Okay, so there will be electrostatic force of attraction, and this force of attraction is provide the necessary centripetal force so that this charged particle can move in a circular path. So the Coulomb force F vector between the two is, they are asking us to find out the Coulomb force of attraction, and they are calling this to be R vector. Okay, they are calling it to be R vector. Now I can write down the force now. So force F is what? K Q1 Q2. So both the charges are same, so K into E divided by distance square. So distance is R square. Okay. Now I have to write down in vector form. You can see everywhere vector is written. So my answer should be in vector form. So if this is your R vector, but the direction of force here is what? This is the direction of force inward. So that is in the negative side of R vector. So this should be minus R cap. Okay, this should be minus R cap. So the force which is acting on that electron is K into E upon R square into minus R cap. So that is K E square by R square minus, and this is R cap, and R cap can be written as R vector divided by mod of R. So this is minus K E square by R cube into r vector. Okay, so this is f vector. So minus ke square by r cube into r vector. Again I can see that the correct option is D. See, this is wrong, this is not in vector form. This is unit vector ke square by r square r cap. This would have been correct, but again the problem is that minus sign is missing here, so that's why it's wrong. So again the D option is correct. So we have to take care of the magnitude part. At the same time we should be very cautious about the direction. So an electron is moving around the nucleus of an hydrogen atom in a circular orbit of radius r. The Coulomb force on the electron, the question can be the Coulomb force acting on the electron is. So the Coulomb force acting on the electron is this one. If I am saying what is the force acting on this nucleus, then it should be in the positive r direction. Okay, that should be, the direction should be plus r cap. The direction should be plus r cap. So this is the force acting on electron. Moving to the next question. It is given that the point charges 4q minus q and plus 4q are kept on the x-axis at point x equals to 0, x equals to a and x equals to 2a. So let's draw the axis first and let's see where the charges are placed. So this is x equals to 0, and on x equals to 0 the charge placed is plus 4q. So plus 4q charge is placed here. Then we have the next point as x equals to a. This is x equals to a point, and here the charge placed is minus q. Okay, very good. And then x equals to 2a. This point will be x equals to 2a, and here the charge placed is again plus 4q. This is the arrangement of the charge. And what they are asking, they have given us the force statement and we have to check them. Only minus q is in the stable equilibrium. All the charges are in stable equilibrium. All of the charges are in unstable equilibrium. None of the charges is in equilibrium. Okay, okay. So let's discuss one thing. They are asking us to find out the condition of equilibrium, whether it is in stable equilibrium or not. So what do you mean by stable equilibrium? Stable equilibrium means the net force should be 0, and if the particle is displaced from its initial position and then it is released, then after some time it should come back to its original position. If it is happening like that, okay, when a charged particle is disturbed slightly and it is released, then after some time if it is coming back to the original position, in its initial position, then I will call that the charge was in the condition of stable equilibrium. And if after slight disturbance the particle goes away from that initial position and does not return back to its original position, then the particle was in unstable equilibrium. Okay, then it was in the condition of unstable equilibrium. So we have to check what is the condition here. So let's say, what is the initial situation? If I'll see the forces acting on this charged particle, so one force is acting because of 4q and it will be repulsive in nature. One force is acting because of minus q and it will be attractive in nature. So this particle is going to experience some force, okay? And if I'll just move it here and there, this distance will change, the forces acting on it will change, and I can see that between these two equal charges 4q and 4q, if it is slightly disturbed, then it will not come back to its original position. So this is not the case of stable equilibrium, and it will happen with all the charges. Okay, so what should be the correct answer? Can you think of it? Can you think of it? What is the correct answer? So now just see here, the correct option is C for Chennai. All the charges are in unstable equilibrium. All the charges are in unstable equilibrium. Let's say why? Because when the charges will be slightly disturbed from their position, then they are not going to return back to its original position in all cases. So if it does not return back to its original position in all cases, then definitely this is not stable equilibrium. So all of the charges are in unstable equilibrium. All the charges are in unstable equilibrium. Moving to the next question. 2 point charges minus q and plus q are placed at a distance of L as shown in the figure. The magnitude of the electric field intensity at a distance r, where r is very large as compared to L, varies as. So you can see that it is the given situation, it is given that r is very large as compared to L. So I am taking a point here, and this distance I am calling as r, and it's given that r is very large as compared to L. So if this r is very large as compared to L, then this is the case of an electric dipole. This minus q charge and this plus q charge are placed at some separation L, and from the center of this dipole, if I am taking a point at very large distance, then electric field at that point can be derived by writing the electric field due to the plus q charge and electric field due to the minus q charge, and then solving to find out the net electric field. The result comes out to be, so basically this is an equatorial point, axial point. I'm really sorry. This point is an axial point for this electric dipole, and on axial point the electric field comes out to be 2 kp by r cube. The electric field comes out to be 2 kp by r cube. So this is a direct formula that you have to remember. On an equatorial point, the electric field is kp by r cube. On axial point, this is 2 kp by r cube. This is electric field. So the magnitude of the electric field intensity at a distance r. So that electric field at a distance r is what? Is proportional to 1 by r cube. So B is the correct answer. So direct formula based question. It was asked in NEET exam. It's a direct formula based question. And you can also remember this formula, that on an equatorial point the electric field is what? Kp by r cube. And this is on axial point, and that is equatorial point. This is an axial point and this is equatorial point. On equatorial point it is kp by r cube, and axial point it is 2 kp by r cube. And let's say this is minus q and plus q. One factor is defined as electric dipole moment, and electric dipole moment represented by p vector, and this is charge multiplied by distance. This distance is, let's say, 2a. So this is q multiplied by 2a. And what is the direction? Direction is always from minus q to plus q. Electric dipole moment is a vector quantity, and its direction is defined from minus q to plus q. So this is the direction of p vector, okay? This is the direction of p vector. And if you have to write down the electric field at some general point theta, the distance is r, electric field at this point, that will be written as kp by r cube under root of 1 plus 3 cos square theta. If I am not wrong, kp by r cube under root of 1 plus 3 cos square theta. So in case of axial point, this theta will become 0, this will become 1 plus 3 4, then this will become 2 kp by r cube. In case of equatorial point, this theta will become 90, this term will become 0, and this is correct. Okay, so this is the correct expression. Electric field at a general point, you have to remember this formula. Electric field at a general point which is at angle theta, distance is r from the center, electric field will be written as kp by r cube into under root of 1 plus 3 cos square theta. So you can remember that expression, okay? And the answer to this problem is B option, B for Bombay. Now again a theoretical question, that if a dipole is placed in an electric field as shown in the figure, in which direction will it move? So a dipole is placed here and this is the electric field. So you can see here that here and here the area of cross section is large. Here the area of cross section is small. So here the electric lines are present in smaller area, and here the same amount of line are crossing through a larger cross sectional area. So I can say that, let's say this point is A and this point is B. So electric field intensity at A is greater than electric field intensity at point B. So electric field intensity at A is large as compared to electric field intensity at B. So the charges are equal in magnitude. So this charge is going to experience a force in this direction, which is a larger force. This charge is going to experience a force in the opposite order, okay. This is going to experience a force in the opposite order. So FA is greater than FB, okay. FA is greater than FB. Because this force A will be what? Charge multiplied by electric field at A. This will be charge multiplied by electric field at B. But electric field at A is greater. So this force will become greater and this force will become smaller. So on this dipole there are two forces acting, FA and FB. But FA is greater na, as compared to FB. So this FA is greater. So this entire dipole should move in the direction of FA. So what should be the answer? Toward the right side, its potential energy will increase. That's also true. That's also true. Because in this case the potential energy is negative. As it goes in the direction of this one, in the direction of electric field, its potential energy will start becoming zero. It will tend towards zero. So basically it's increasing from minus to positive. So this C option is correct. C for Chennai is the correct answer. Done. So these are some of the questions that I have discussed. Again we have one more question. Let's see this. A thin conducting ring of radius r is given a charge of plus q. So I have given a plus q charge on this entire ring, okay. So since it is a conducting ring, this charge is going to distribute uniformly on the surface of the ring, okay. So uniform distribution of charge will take place. Now the charge will distribute like this. Now the electric field at the center O of the ring due to the charge on the part AKB. So just because of this part, just because of this small portion, one quadrant, the electric field at O will be where? Is E. Because of this part the electric field is E. And any direction is given. And the electric field at the center due to the charge on the part ACDB will be what? Okay, okay. So because of this part they are saying the electric field will be E. And what will be the direction? Because of this part the electric field at this point will be in this direction. It will be in this direction, okay. And the net electric field at the center should be 0. So now they are asking us to find out the electric field due to the remaining portion, this portion. We have to find out the electric field due to this green part, okay. You have to find out the electric field due to this green part. So if the net electric field here have to be 0, and because of this yellow portion the electric field is E, so because of this green part also the electric field will have to be E. But the direction should be like this, okay. But the direction should be like this. So if they are calling it as KO, this point is K and this point is O, so they are calling this direction to be KO. So for this one the direction should be from O to K, right? It's OK. So the direction of electric field will be E. magnitude will be E, and the direction will be from along O to K. So KO will be wrong, OK will be the correct, but it will not be 3E, it will be E only. So B for Bombay is the correct answer to this problem. I hope you understood this question. Because the net electric field at the center have to be 0, right? Because the total electric field at point O, because of this green part and because of this yellow part, have to be 0. So if this electric field is E here, so this also have to be E, and it should cancel it, right? Then only it will become 0. So if it is E along KO, it should be E along O to K. So that magnitude wise they are equal and direction they are 180 degree opposite to each other. So the net will become 0. So guys, that's all from my side for today's session. So I tried to explain some of the concept, some of the question based on this concept. So just revise properly, revise this chapter, and I have given you some key insight from this chapter. So it will help you to revise, remember all the formula, practice some of the questions, and if you face difficulty solving any problem, I really will appreciate that you take the photo of that question, put in the comment box, and definitely I'll try to solve that question for you. Thank you guys, bye bye. We'll see you tomorrow for the next session of the Power Hour series. Thank you. Till then, bye bye, good night. Take care of yourselves.